Boa tarde a todos. Good afternoon all. Então, estamos aqui hoje para a defesa de doutorado do aluno Caio Ciardelli, tá, com um trabalho intitulado Adjoint Tomography of South America based on 3D Spectral-Element Seismic Wave Simulations. Os orientadores são Marcelo Assumpção, tá, do Departamento de Geofísica do IAG.USP, e os co-orientadores são Sousa Vanderly, da Northwest University, e a doutora Ebru da Colorado School of Mine. Tá? Caio vai ter 60 minutos para fazer a apresentação, tá? Não pode estourar esse tempo. E depois a arguição, o tempo de arguição, o máximo são 4 horas, tá? Então, também não podemos ultrapassar esse limite de tempo. Então, temos 60 minutos de apresentação e 4 horas de arguição. So I was just explaining to Caio that he has 60 minutes to the presentation, and after this presentation, we follow to the question session. So, Caio, you can start now. Okay. Thank you all for joining us, and now it's your time, Caio. Good luck. O seu áudio está fechado, Caio.
I'm sorry. Just to make sure, can you see my screen? Okay.
Yes. Yeah, put in the full form.
Yes, full screen now?
Yeah.
Okay, so thank you all for coming for my PhD defense. This was a especially challenging project. It was developed in cooperation with the Colorado School of Mine and the Northwestern University. And I have learned a lot. And it actually is not a single project anymore. Over the course of the last 5 years, it has branched out into several side projects. And I will show you the results now. So from the beginning, how do seismologists know what is inside the Earth? For instance, how do we know there is an inner core surrounded by a molten outer core? And we know because seismograms, they convey information about the source mechanism, the medium through which seismic waves propagate, and the receiver. But we know the receiver response because when the receivers come from the factory, a response file comes along, so we can remove the receiver response. So in general, if we know the source, we can try to infer the medium, or if we know the medium, we can try to infer the source. Our region of interest is South America. So South America can be broken down into 3 major domains. The South American platform in green, the Patagonian domain, and the Andean belt. The South American platform can be further divided into the Amazonian domain and the Brasiliano domain. And inside the stable platform, we see the Rio de la Plata craton, the San Francisco craton, and the buried Parnaíba block and the Paranapanema block. And the major structure is by far the Amazonian craton, and the Amazonian craton is usually divided in 2 halves, the Guiana Shield and the Central Brazil Shield. And a widely accepted model for the formation of the Amazonian craton tries to classify it into several geochronological provinces according to their age. So the oldest geochronological province is the Central Amazonian from the Archean period, but there's also the Maroni Itacaiunas, Ventuário Tapajós, Rio Negro Juruena, Rondônia San Inácio, and Sansás Aguapeí. And they get progressively younger over time. Sorry, my screen is out of control. We are also interested in the Nazca's lab. these two figures show the Nazca slab plunging. This is the slab 2 model. And we see that the dip angle varies along the subduction zone. In some regions, the slab is steeper. In others, it tries to horizontalize. And this is mainly controlled by the age of the slab. The older the slab, the denser it is, and the faster it shrinks into the metal, it plunges into the metal. Our data is mostly composed of two sets. We have the CMT files. CMT files, they represent the source mechanisms. We have 112 earthquakes altogether. They are surrounding our entire region of interest because we want a reasonable ray coverage. And the colors denote the depth of the events. So red events are shallower and violet events are deeper. And with the source mechanisms, we can simulate each of these earthquakes using a numerical method. We also have more than 1,300 stations. All stations I could find, they are there. And again, the color is related to the station elevation. We have even some ocean-borne stations here and some stations over the Andes. The station coverage is not even, so stations are not even distributed. And we have to compensate this. Otherwise, we can create numerical artifacts in our model. And this also tends to slow down the convergence of our inversion. So to compensate this, we use this weight from 2019. And the more isolated a seismic station or an earthquake is, the larger the weight it receives. So if you have a cluster of events, they are weighted down. It's an attempt to compensate the uneven station distribution and source distributions. To simulate our synthetic seismograms, we use SpecFan 3D Globe. This is a very powerful software. It's not only a single code, it's a toolbox for numerical simulation. And it uses the Spectral-Element method. I don't have time to explain the Spectral-Element method into detail, but all those numerical methods, they somehow try to discretize the Earth's interior. And for the global version of SpecFan, the globe is divided into 6 chunks, and each of these chunks are composed of many spectral elements. And for my simulations, I only need a single chunk. And in this chunk, there is a model superimposed, a velocity model. The red regions, they denote lower velocity, at least lower than average velocity, and the blue regions denote higher than average velocity. Usually, we interpret these velocity variations as a kind of thermal anomaly, but they can also be caused by composition. And you can see, perhaps you can't because of the screen resolution, but the mesh resolution increases upwards. So we need a lot of spectral elements to fully honor the crust, but we can decrease the resolution towards the inner core. Here is more clear. So for the crust, there is a denser mesh. There is a transition layer, call it doubling layer, and a lower resolution mesh below. And spectral elements, they are very accurate. And they were benchmarked against normal mode simulations. Normal modes, they are almost analytical, or perhaps fully analytical, I'm not sure, solutions for the wave equation. So they are exact. And in this simulation, the effects of the attenuation and the Earth's self-gravitation were included, and we can barely see the difference between the seismograms. So it's very accurate. But unlike normal mode simulations, spectral elements can also explain the surface topography very easily. And once you have your synthetic seismogram and your observed seismogram, the first step is making sure that you don't have noise in your inversion, because we are carrying out full waveform inversion. We are using the entire wave information. We're not using the travel times. So even a small amount of noise can really damage our inversion. And we developed a multi-step algorithm to get rid of the bad components. For instance, this first component, there's clearly a problem here because the amplitude of the synthetic seismogram is way larger than the observed seismogram. So the algorithm just discards this component right away. We can also look at the time before the P wave arrival or the first arrival. And ideally, there should be no signal in this region. So we can use this region to measure the signal-to-noise ratio. After this two stage, there is a third stage in which we divide the region into several smaller windows. And inside each of these windows, we compute the mean energy. So the height of these bars, they represent the energy. When the red bar is larger, it means that the mean energy of the synthetic trace is larger than the mean energy of the observed trace. And if this ratio drops below a certain threshold, which is 0.35, we discard the window. And if not, the window is accepted in green. And if we discard a certain number of windows, the code understands that there is too much noise in the seismograms and rejects these components. But getting rid of the noise is not enough because usually we cannot fully explain the entire seismogram. So despite the name of the method, which is full waveform inversion, we almost never can use the entire seismogram. So high frequency surface waves are hard to properly model. The tail of the seismograms is also hard. And our inversion method has some limitations. So if the phase difference or the amplitude difference between the two signals is too large, we cannot invert the signal. So even if this difference is really caused by an actual geological anomaly, we cannot invert this. So we have to select some windows in blue in which there is a reasonable agreement between the observed and the synthetic seismograms. There has to be some difference because if you won't select where they are identical, then there is no purpose in doing this inversion. Your model is already good enough. But it's somehow a subjective decision, which data you include and which data you throw away. There are several types of measurements. The easiest one to understand, in my opinion, is waveform measurement. Waveform measurement is just the residual between the observed and the synthetic seismogram. So we simply subtract the two signals and we get what is called the waveform adjoint source. But we can also use the envelope of the signals to make our measurement or the instantaneous phase. And in the instantaneous phase, what we are doing is separating the phase information from the amplitude information. We do that by using the Hilbert transform. And the reason for removing the amplitude information is because most of the nonlinearity of the inverse problem comes from the amplitude information. And also because usually amplitude data is less reliable, so you have to be careful. It doesn't mean that we cannot use amplitude information. We should use amplitude information if you are trying to constrain the Earth's attenuation, for instance, but it's harder and you have to be careful. And the instantaneous phase has some advantages over other methods. For instance, you can also measure the phase difference using cross-correlation, but cross-correlation requires several smaller windows. You cannot use a single large window to make a cross-correlation measure. And instantaneous phase can handle large windows. But even instantaneous phase has some limitations because if for some reason, even using the window selection algorithm, the phase difference between the two traces is too large, you can have cycle skips. And cycle skips create spikes in the adjoint source. And spikes are not really good for numerical simulation, so we don't want that. But there is a solution for this, which is the so-called exponentiated phase measurement. And the exponentiated phase measurement is a different way to estimate the instantaneous phase difference. And they are almost equivalent. So the exponentiated phase measurement is actually the instantaneous phase measurement with a sine function applied to it. So I have demonstrated this, and this publication was the first one in this project. Once you have your adjoint source, you can use the adjoint method to compute the gradient. This is the gradient of the misfit function, is the gradient we need to update our velocity model, to improve the velocity model. So we begin by carrying out the forward simulation with our starting model. Using our forward simulations, we get the synthetic seismograms, we can make our measurements. And making our measure, we create the adjoint source. The adjoint source is then injected at the receiver location and creates a secondary field. This field is called the adjoint field, and it propagates backwards in time. If you correlate the forward field and the adjoint field, you can compute your sensitivity region, the so-called sensitivity kernel. The sensitivity kernel resembles a banana, and it is crucial for updating our model because it highlights the regions inside the planet in which any perturbation would change our seismograms. And the shape of the sensitivity kernels are related both to the measurement you are doing, the kind of measurement you are using, but also to the wavelength. So the shorter the wavelength, for instance, here we have two amplitude kernels, so they are showing the amplitude sensitivity of the seismogram to a perturbation in the model. And we see that the beta kernel, which is the sensitivity kernel for an S wave, is thinner than the alpha kernel. And that's because the wavelength of the S wave is shorter. So the shorter the wavelength, the more your kernel approximates the travel time predicted by ray theory. So this is the ray path in green. And if you are in the infinite frequency regime, your kernel shrinks to 0, and you actually recover the ray path. And you can also compute the travel time kernel. And the travel time kernel has a paradoxical structure because it is hollow in the middle. So this was very hard to understand first time it was observed, and nobody really understood what's going on. But several papers were written about this, but even after reading them, I still didn't understand. And I wanted some further insight into this problem. So I decided to create a simplified version of the sensitivity kernels, trying to understand what was going on. And when you have a wave, not necessarily a seismic wave, it could be a light wave or a sound wave. This wave does not take any path. There are some special paths to be taken. And those paths are given by the Fermat's principle. They have to be stationary paths. A stationary path is a path in which, if you change the path just a little bit, the travel time almost doesn't change. So you could take all those paths, but for a homogeneous medium, only the least time path would be taken. The straight line would be taken, because in homogeneous medium, a straight line is the least time path. But not necessarily the least time path. There is also the maximum time path. For instance, the PP wave or the SS wave are maximum time paths. If you perturb those paths, the travel time would increase, not decrease. And why is that? It's all related to wave interference. So if you allow waves to travel through all the conceivable paths, they will constructively interfere at your receiver. Some waves will arrive in phase, some will not. And when they arrive in phase, you get constructively interference. When they are out of phase, you get destructive interference. For waves traveling through stationary paths, all waves near to the stationary path, they will constructively interfere. And all the other waves tend to cancel each other out. So in the end, only the stationary paths survive. Those are my simplified model for the amplitude kernels. They are straight structures. There is no curvature here because they are just a simplification for the problem. But we still can see that as we decrease the wavelength, the kernel shrinks. And it also shrinks when we approximate the source and the receiver. And when source and receiver are very close and the wavelength is very, very short, we are beginning to recover ray theory. And our travel time kernel has the same behavior, but it is also hollow in the middle. I don't want to give a brief explanation for this in this presentation, but I am about to submit a paper in which I am explaining this into detail. So what's going on? Because after those experiments, I really understood what was going on. This paper is currently being reviewed, Professor Ruschnieder, and we are about to submit it to the European Journal of Physics. Back to our main project. If you are using gradients, and you have to use gradients because we cannot afford a global search method or genetic algorithms because the forward simulations are really expensive. So we need a fast convergence. So we need to use or either Newton methods or Newton-based methods or some kind of gradient method because we don't have enough computational power. But one issue with gradients is that you can get stuck into a local minimum. And one way to try to mitigate this problem is by beginning your inversion using only the long period information. So if you have only the long wavelengths in the beginning, then your objective function tends to be smoother, and you can reach your minimum more easily. And after that, you can gradually increase the frequency content of your data. This is the multi-stage approach for our full waveform inversion. So we begin with long wavelength information, then we add intermediate wavelength and small wavelength information. This is M00, our starting model, which is S361, a model from the Harvard University. Using this model, we computed the forward simulation, the synthetic seismograms, the adjoint source, and we found our first gradient. We have to remember that the gradient always points towards the maximum increase in the misfit. But we don't want to increase the misfit, we want to decrease the misfit. So we have to multiply this gradient by a negative constant, usually a constant found using linear search. And once you have your gradient and your constant, you can just add your gradient to your starting model and find your second model. Then you can repeat the process all over again until you find your third model and so on until your misfit is not decreasing anymore. This is the misfit evolution. So first we carried out 5 iterations using data from 50 to 100 seconds. And we observed a significant drop in the misfit. And we recomputed the windows because now that the synthetic seismograms are more similar to the observed seismograms, we can include more data. And when you enlarge your windows, your misfit increases. That's why there is this jump here. At iteration number 7, we decreased the minimum period from 50 seconds to 40 seconds. That shrinks your windows and the misfit decreases. There is a complex iteration between the windows length and the waveform similarity, but in the end, you get those jumps. At iteration number 12, we observed some high-frequency numerical noise in the lower mantle of the model, a region in which we are not expecting short wavelength structure, so we low-pass filtered our model. At iteration number 15, we added a second period band from 30 seconds to 6 seconds. At iteration number 20, we added a third period band from 23 seconds to 45 seconds. And at iteration number 22, we decreased the minimum period from 23 to 17 seconds. And from there on, there was no further decrease in the misfit, so we stopped our inversion. So every time we change the windows, we change the color in this figure. So the color actually denotes the windows we are using. Yes, and the overall drop in the misfit after the 23 iterations was 50%. But this is not a very robust measurement of our model improvement because we are using the same events of the inversion to measure the misfit. So we can also select 53 events not included in the inversion and make cross-correlation measurements. We split our seismogram into several small windows. And for each window, we can make a cross-correlation measurement to estimate the phase difference between the observed synthetic seismograms. For the initial model in black, we see a larger histogram, as it is wider, and after 23 iterations, we see that the histograms, they are narrower, and they are also more symmetrical. So we not only reduced the dispersion, but we also removed a systematic error, some kind of bias in the initial model. We can also use the mean correlation coefficient. So for each source, we can compute the correlation coefficient for all stations, for the first iteration and for the last iteration. And we clearly see an improvement in the waveform similarity for source, and the same thing for the receivers. We can also see that some regions of the model are better explained than the Caribbean is a complex region, so we don't expect as much agreement as in the central part of Brazil, for instance. We also have to carry out some resolution tests because we cannot resolve arbitrarily high frequencies. We add a Gaussian perturbation, and if our method was perfect, if our data coverage was perfect, we should retrieve the same perturbation. But of course we don't. We get some smearing, mainly in the horizontal direction. And this gives us an estimate of our resolution. So for 110 kilometers depth, both in the middle of the Amazonian craton and the Paraná Basin, we get those relatively good resolutions. But as you go deeper, your ray coverage decreases and your resolution gets poorer. It gets worse. So at 111 kilometers depth, you still have a reasonable resolution, but at 2,500 kilometers depth, the model cannot really resolve anything anymore. So any observation at this depth is not reliable. This is a direct comparison between our starting model and the final model. The magenta line is the Nazca slab according to the slab 2 model. There is a very nice correlation in this region. We can also observe the slab window where the Chile region are subducting. The Paranapanema block, the San Francisco craton, the Paranaíba block, and the Amazonian craton, especially the Archean cratonic nuclei. And also the borders of the Argentine Basin and the Borborema province. The same model at 200 kilometers depth, we still see the bottom of the cratons. At 300 kilometers depth, we see the Nazca slab, 500, 700, 900, and 1100 kilometers depth. We are also comparing our model. SAN 23 is South American Adjoint Model Iteration 23 with GLAD M25, which is the last global adjoint tomography. And we see that in the long wavelength, there is a very high correlation between the two models. They are very similar in the long wavelengths. The only difference is that our model has a shorter period information. This book was written by Professor Andrea Bartorelli, Wilson Teixeira, and Benjamin Blay, in honor to Professor Umberto Cordani, a great geologist, and our model went to the book's cover. Some P-wave models, they show a gap in the Nazca slab beneath Peru, but others don't. For instance, here we have a P-wave model and an S-wave model, and there is no evidence for such a gap. And both GLAD M25 and our model also doesn't show any evidence of gap, beneath Peru. Here we have some vertical cross sections of the Earth. In the first profile, we see the Nazca slab plunging directly into the lower mantle very quickly. In the second profile, we have to be careful because we know from the resolution tests that there are some horizontal smearing in our model. So Perhaps this is just a consequence of this mirroring, but it could also be that this lab is being trapped at the 650 seismic discontinuity. We know that there are some mineral phase changes at 410 and 650 discontinuities. They create some seismic discontinuities. We observe them in the seismic data, but they also change the mantle viscosity. And these labs, sometimes they have some problems to penetrate into the lower mantle. They can be sitting for a while over the 650, but as they cool even further, they eventually get denser and denser, and they can shrink. After a while, they will shrink into the lower mantle. In the third profile, from H to H prime, this lab is doing something quite peculiar, and it's not clear how it is plunging into the mantle. So sometimes it seems like it is being trapped at 650, and then it plunges into the lower mantle. But this figure also suggests that perhaps we should not see the slab plunging downward and also forward. We should see only the slab plunging downward. So the slab is just sinking vertically. And it's the trench that is actually moving. So the Nazca trench is moving westward, and the slab is plunging downward. So perhaps this is an indication for that. And the same pattern was observed by Rodrigues et al. The Paraná plume, we are not sure if this is really a plume. What we are sure is that there is a low velocity anomaly beneath the Paraná basin. This anomaly was first observed by Van der Kar and was confirmed by other tomographic models. We also found evidence for this low velocity anomaly. Rodrigues found a very strong signature for this anomaly. And there are two major explanations for this. So it could be that the Nazca slab is losing water, and the water is decreasing the melting point of the lower mantle. The problem with this theory is that we don't expect the slab to have volatiles after so much plunging, because usually the slab dehydrates at shallower depths. So at this point, we don't expect the slab to have any water anymore. The also theory is that the slab is sinking, and as it sinks, it displaces some material, some hot material from the lower mantle, and creates some kind of convection, moving this material upwards. And the reason we think there is some relationship between these anomalies and the Nazca slab is because these anomalies are not only beneath Paraná basin, they are also in the central Brazil and under the Amazonian basin, and they look like they are parallel to the trench. So that's why many people think there is a correlation between the Nazca slab and these anomalies. The stable lithosphere. So we clearly observe the cratons again. The Amazonian craton is a very strong signature. All the other cratons I have mentioned before, but we don't see any signature for the Rio de la Plata craton. And this is not only our model. All the other previous tomographic studies I know about, they also don't show any signature for this Rio de la Plata craton. There's simply no seismic evidence for the existence of this craton. The lithosphere and the asthenosphere boundary, the LAB. And you have to be careful when using a tomographic model to estimate the LAB, because if you are only using body waves, for instance, there is a trade-off between the amplitude anomalies and the thickness of the cratons, or of the lithosphere, actually. So in our case, we are using both surface waves and body waves, so we can decrease this trade-off, and we believe that our estimates are more reliable. What we do is that we compute a vertical 1D profile at any point we want, and we just measure the gradient with that. And eventually there is a maximum change in the gradient or a minimum change. I don't remember at this point, but there is a sharp transition in the gradient, and we recognize this sharp transition as the lithosphere-asthenosphere boundary. And when we compare our results with the receiver function data, the receiver function measurements are in yellow, these yellow dots. And the blue circles are the measurements in the stable region of South America, and the red triangles are the measurements over the Andes. And there is a very strong correlation between our LAB and the receiver functions measurements. This correlation is even stronger than the correlation from another model, and this model was a mechanical estimate for the LAB using geochemical and geothermal data. So it was a surprising result. I was not expecting that we would have such a good agreement for our LAB, but we found it. The Amazonian craton is very interesting. And for each of the geochronological provinces, we have computed the mean perturbation, the mean velocity perturbation. What we want to check if the correlation between the age of the craton and the strength of the anomaly. And we do find a very strong correlation, both when we look at the delta B, which is the mean velocity anomaly, with the age, and also with the LAB and the age. There is a strong correlation. And this is a bit hard to explain because we know that after 500 million years, the cratons, they are not cooling anymore. So if we were to consider only the residual heat from the craton formation, there should be no difference. But this is only due to the natural cooling. Doesn't mean that the cratons cannot be at different temperatures. Indeed, we found a recent paper published a few years ago has shown that there is a 200-degree difference between inside the Amazonian craton. But this could be, for instance, caused by a asthenospheric flow hitting the craton from the west to the east. But even this thermal difference is not enough to explain this velocity anomaly. We also need compositional changes. So perhaps the older regions of the craton, especially the Archean block, is more iron depleted. We know that iron can reduce the seismic wave velocity because it simultaneously increases the density and decrease the rigidity of the plate. So iron depletion can also explain this. So maybe it's a combination of iron depletion with thermal differences to explain these anomalies. This publication was submitted to DJR, Solid Earth. And okay, so you have your model. Now what? So you want to share your model with other researchers because people want to use your model for other studies. And the binary files we use to run the numerical simulations, they are a nightmare to create any figure. In SpecFan, we can use ParaView because there is a routine to combine these files into a VTK file. And we can visualize them using ParaView, which is great. But other people don't have access to clusters. They don't have, maybe they do, but we don't expect them to have. And they also cannot afford to download maybe 50 gigabytes files. The files are visually incomprehensible for anyone not very used to work with them. So we need a better solution. And it's not anything new that global velocity models can be represented using spherical harmonics. But we can use a combination of spherical harmonics and B-splines to create a 3D expansion. So we are not just expanding spherical shells and then interpolating these spherical shells. We are actually computing a 3D expansion of our model. This is a synthetic example showing the degree 0 of the expansion. This is a horizontal cross-section showing the equator, how the Earth is from within. For degree 10, we can recover the anomalies at the equator very well. but not at the poles. With degree 20, we can include more higher frequency content in the model. And as we further increase the degree, we can improve our expansion progressively. The cubic splines, which we use it to expand the Earth in the radial direction, they are not evenly spaced. This is one of the advantages of using B-splines. They can be denser in regions of high complexity, such as the upper mantle and the transition zone, and they can be more spaced in the middle of the lower mantle, where you don't need a very high resolution. But even using B-splines, we have to be careful because, for instance, we have the 410 and the 650 seismic discontinuities. You cannot use a single spline crossing the discontinuity because this is a zero-order discontinuity, and splines, they don't like it. They behave like Fourier series at first-order discontinuity. There are some spurious oscillations. So we cannot expand this first-order discontinuity. So we actually have to carry out separated expansions for the upper mantle, the transition zone, and the lower mantle. But still, the upper 80 kilometers of the model, which is the crust, cannot be handled using spherical harmonics or B-splines. And why? Is because the crust is extremely complex. It has a very high frequency content, spatial frequency, not temporal frequency content. And it also has topography. The mesh is highly complex. We have these doubling layers. This is excellent for numerical simulations, but it's a big problem if you want to expand your model. And we cannot expand this region using spherical harmonics or any other kind of smooth functions. So one possible solution is using a block model. Is a simple solution. It works, and we can do that. And that's how we expanded both Gladium 15 and Gladium 10.5, the upper regions. And we use a combination of a block model with a spherical harmonic expansion. Once you have this expansion, which is just a few hundred megabytes, you can very easily download a set of serial routines. You don't need a cluster anymore. You can run this using a single core in your laptop. And you can create this very beautiful depth slice using GMT6. We provide the scripts for plotting as well. This is a depth slice at 10 kilometers depth of the crust. We also showing the transverse isotropy in the upper mantle. And since we are using spherical harmonics, we can expand our model up to the degree we want. So if you want to look into the low frequency content, you can just expand up to degree 10, for instance. This can be very useful if you want to compare your model with a normal mode velocity model, for instance. Or you can fully expand your model up to degree 100, let's say, depends on the model. For Gladium 25, we use it much higher degrees. And you will perfectly recover your model. Not perfectly recover. Of course, there are some limitations. For instance, there is topography at internal discontinuities. The 410, the 650 discontinuities, they also have topographies. We cannot expand these topographies. We have to remove these topographies. But it still is a very good representation. You can also look into the vertical cross sections. You can look at the absolute velocities or to the anomalies, velocity anomalies only, whatever you want. Here in gray, we have a representation of the topography. Of course, it's exaggerated, but this is useful. Sometimes you want to, for instance, you want to observe a slab subducting into the mantle, and it's very useful to know where your trench is. We can also look into power spectra. If you have a spherical harmonic expansion, you can expand your model. Actually, we already have the coefficients for the expansion, and you can use these coefficients to compute power spectra. So S3620, for instance, goes up to degree 18. So there is a sharp transition, doesn't have any energy after 18 degree 18. And Gladden 15 added a lot of frequency content to high frequency content, to the starting model. And Gladden 25 has an even higher frequency content. And we can see in both power spectrums, the power spectrum by depth and the overall power spectrum for the whole mantle. Remeshing is also very important. We gradually increased the frequency content of our simulations, and high frequency simulation also requires a higher resolution mesh. So you have, at some point during your iterations, unless you have a lot of computational power and you can begin using a high resolution mesh from the first iteration on, eventually you will have to interpolate your mesh. And we also wrote a routine for mesh interpolation. There was a routine in SpecFang, but we put a lot of effort trying to make some adjustments, trying to fine-tune the interpolation parameters to get as much accuracy as possible. And Gaussian smoothing is also very important. In each iteration, we have to smooth our kernels, because although we filter the adjoint source, we can still have some numerical noise in the kernels. So you have to smooth your kernels. And sometimes you even want to smooth your model. In our case, I said that in iteration number 12, we found some numerical noise in the lower mantle. And to get rid of that noise, we had to apply some kind of low-pass filter. And we used Gaussian smoothing for that. So you can vary you can have a different horizontal smoothing and vertical smoothing. And you can also vary your smoothing with that, because usually the deeper you are, the more smoothing you need. But one problem with applying Gaussian smooth to a model is that you can destroy the internal discontinuities. But there is an option in the routine to preserve the discontinuity. So we just smooth each zone separately. So we carry out a filtering for the lower mantle, another filtering for the transition zone, and another one for the upper mantle. Like this, we can preserve the seismic discontinuities. This third publication went to the Computers and Geosciences. It was recently came back with some minor review suggestions, and the toolbox is already available on GitHub. I am about to commit some major change, some improvements to the toolbox, but it's already operational and you can download it and use it. We also developed 14 Jupyter notebooks to explain the theory into detail. For instance, there is a notebook for B-splines, a notebook for spherical harmonics, and that's because usually most papers already assume that you know some background information, but some people don't. And so we try to make our paper somehow standalone. So by using the Jupyter notebooks, you should be able to understand everything that's going on. And we thank FAPESP for the PhD grants. The FAPESP is funding me from 2016 until very recently. I also thank Quest High Performance Computing at Northwestern University. Quest is an excellent cluster. It served me very well for my project. Also, the Oxford Submachine for display of tomographic models, and GMT6 and ParaView, which are two excellent and very powerful software. And yes, and of course I have to thank my advisor, Professor Marcelo Assumpção, for everything he has done for me. My two co-advisors, Professor Ebru and Professor Suzanne van der Lee. I would never accomplish everything I did without their help. I thank everyone. I thank my family. I thank my friends. Thank you all for this. So that's it.
Thank you, Caio, for your excellent presentation. So before starting the questions, I suggest that we have a very short break, about 5 minutes, so 5 or 10 minutes, so that Caio can can drink some water. People can have some coffee. What do you think, people?
Yeah, 5-minute break is great.
Okay, that's great. So in 10 minutes, we'll be back.
Sure.
Você acredita que eu esqueci de começar a cronometrar? Aí, quando você começando a começar a cronometrar, eu parei durante 40 minutos. Eu falei, puxa, acho que deu 45 certinho, deu 50. Perfeito. No final, eu comecei a falar mais devagar, para tentar
Caio?
Yes.
Are you ready? Okay. So we should move on. I would like to invite Ebru. Was that? To start
Eu não estou escutando nada, vou ter que sair e entrar de novo, está certo? Há um problema com o meu computador.
Okay. I wait. Now, can you listen? Oh, you are muted. You are muted.
No, I'm not. Okay, so yeah, everything is fine now. For some
Okay,
reason,
that's great.
that happens when I teach online as well, and I just have to leave the room and enter again.
Oh, yeah.
Don't ask me why.
Yeah, it's no problem. No problem. So I would like to invite Ebru to start the questions for Caio. So Ebru, thank you for accepting the invitation for this defense. So the time is yours now.
Yeah, thank you. Can you hear me okay? Okay, great. So Caio, first of all, congratulations for this very nice study. I already knew your study and thesis very closely, but still it's pretty exciting to see it in the thesis format. I'm sure you are going to receive a lot of questions related to the tectonics and geology and geodynamics of the region. So I will mainly focus on more theoretical and technical aspects of your approach. So first of all, let me start with this question. Why did you choose adjoint methods? What did you expect from the beginning by choosing adjoint methods and numerical simulations? And what are the advantages and disadvantages of choosing this approach to construct a new model for the region?
Well, honestly, when I began this project, I didn't know what the adjoint method was. So in the beginning, all I knew is that waveform inversion was the state-of-the-art method for seismic inversion. And over the course of the years, I put a lot of effort in understanding the theory and what was the advantages and disadvantages. And over these years, what I learned is that mainly due to the finite frequency effects, usually we have to be careful when using ray theory. So it doesn't mean that ray theory can never be applied, but we have to be careful. And by using finite frequency kernels, we can relax some of these constraints. Besides, SpecFan is a very can create very accurate synthetic seismograms, so we can fully honor the crust. We don't have to worry about crustal corrections, for instance. And I carefully selected my data set, and my goal was to increase the resolution of South America. I wanted to see shorter wavelength features in South America. And we achieved this for the cratons. I think we have imaged the cratons with the highest resolution I have ever seen for a regional model. The result was not so great for the Nazca's lab. We have some horizontal smearing, but overall, I think my goal was achieved. So yes, I was expecting a new model for South America. I didn't knew how much this model would change in relation to the previous model, but yeah, that's it. I think that's the answer.
So basically, you expect to have higher resolution by using 3D simulations.
Yeah,
in your words, by computing accurate seismograms. But do you think that numerical methods always provide you accurate seismograms? What
No.
should you be careful?
Yes.
And what is the limitation?
Well, we have several limitations. So in the case of spectral elements, one limitation, of course, is computational power. There is a minimum period we can simulate. In my case, it was 17 seconds. I could not go below 17 seconds without additional computational power. But there's also the data limitation. So it doesn't matter if you are running 1 Hertz simulation if you don't have enough stations. You need station coverage. And that's why I used as much stations as I could from the beginning. So this is another limitation. We have noise. Yes, I think the major limitations right now is data and computational power. So I wasn't sure because when you are doing adjoint tomography, you have to be much more rigid with your choice of the seismograms. If you are doing travel time tomography, you can use thousands of events. You don't have such a high quality events. You don't have such very straight restrictions for the magnitudes. But on the other hand, you have you are only using some travel times inside the seismogram. When you have the full waveform inversion, you can extract much more information from each seismogram, but on the other hand, you have less seismograms. So from the beginning, I wasn't sure in the end what would be the effect of using less seismograms, but higher quality data and extracting much more information from each seismogram.
But you could always use more earthquakes, right?
Yes.
The number of seismograms.
Yes, but of course that if you increase the number of earthquakes, you also increase the computational cost of your simulation. And it doesn't matter if you are running 10,000, if you are using 10,000 stations or a single station, the cost is almost the same. But as you increase the number of earthquakes, your computational cost also increases. And there's also the restrictions of the quality of the CMT files. I downloaded over more or less 300 CMT files because the first stations we have data in South America was from 1995. And inside this set of seismograms, I try to choose the most representative seismograms. So at this point, perhaps adding more CMT files wouldn't change the result that much because we already have a reasonable coverage. So maybe we would only marginally improve our resolution by adding more CMT files.
So you mean there would be redundant data?
Perhaps.
That may contribute much.
Yes,
so
perhaps.
Do you think that there is no point, because nowadays there are tomographic models which are using classical methods or classical ray theory or using analytic finite frequency kernels, and they are almost making use of the entire CMT catalog, or they are using millions of earthquakes. Do you think that there is no point of doing this, or do you think that we might be able to get the same model with a subset of events as long as you have a similar coverage?
Well, when I was thinking about the number of earthquakes, I was thinking in the difference between 112 and 300 earthquakes. But if you have millions of earthquakes, then it's a different story. Perhaps your result would change. So I think the only way to make sure is actually...
But the source and station locations are the same.
Yes, they are. So they are. So my first guess would be that you would find, maybe you would find some improvements, but only marginally improvement. If you already have enough CMT files to represent your region, then adding more and more data won't contribute that much to improve your model even further.
So assume that you have infinite resources. You have infinite computational power. and you have access all data. But of course, in the current data source configuration, what would be your strategy to further improve the resolution of South America or anywhere else on the globe? If you would like to perform tomography, what else would you change in your current approach? Or what should be the right way for you to further improve the resolution of tomographic images?
Okay, first of all, if I had limitless computational power, I would not be using gradient method. I would carry out a global search, because by doing a global search, I would be sure that I would find the global minimum. So this is the first thing I would change. But about the resolution, of course, we have the smoothing, because on each iteration we are smoothing our gradients. Perhaps I didn't have to use such a large smoothing. Perhaps I could reduce the smoothing a bit further. That would be one thing. Maybe we could try double difference, adjoint sources. What else? So yes, decrease the minimum frequency. Of course, I would decrease the minimum frequency, but there's a limit. If you are not changing your data set, if your data set is still the same, it doesn't matter how much computational power you have.
You have additional data. I mean, assume that you have all the resources. You also have the money. It's,
okay.
What else is needed?
Okay, well, certainly a major problem we have right now is that we don't have stations covering the ocean. So we have to add stations in the oceans. This is a major constraint. I would certainly use a global simulation, not a regional simulation, because I would have the core phases to improve the vertical resolution. I had some smearing in the horizontal direction, and I think it's because most of my kernels were in the horizontal direction. So if I had phases coming from the inner core or the outer core, the resolution would certainly improve. So yes, I would install stations all over the planet. Even if you have limitless resources, you can even put stations inside the mantle itself. And that can certainly improve the resolution.
So you said, okay, data is one aspect. And if you think it, you said something like, I would prefer a global search.
Yes.
As an inversion strategy. What do you mean by that?
A global search means that you would try all possible models, like trillions of trillions of trillions of models. And for each of these models, you can compute your misfits. And by doing that, you can make sure that your model is really the model with the minimum misfit. And not only that, if you can compute all your models, you can actually map your objective function. So you also know the uncertainty of your final results. Because right now we can estimate the resolution using the point spread function, but if you have limitless resources and you can compute a global search, then you have access to your entire objective function. So you are sure that you have your global minimum, and you know the uncertainty of this minimum.
Is the point spread function tests, are they the only way to assess the resolution? Because actually they don't say anything about uncertainty, right?
Yes, they only say
what can you do right now for uncertainty quantification?
To quantify the uncertainty?
Or can you do anything?
Well, that's a problem because we have many sources of uncertainties. We have the theoretical uncertainty of our model, which is mainly based on the random fluctuations of the data, random errors, but we also have systematic errors. For instance, we have errors in our CMT files. Our CMT files are not perfect. We are not perfectly simulating the earthquake. So maybe we could also improve our CMT files. If you have perfect CMT files, you would eliminate one source of error. And that's one thing. So to really know your uncertainty, you have to take into account all possible sources of uncertainties in your model. Everything that you are assuming, every single approximation.
Yeah, that's correct. I mean, to be able to eliminate or to minimize the trade-off between the parameters, most likely you should explore ways to also incorporate reducing the uncertainty in source parameters, or maybe there are other factors. For instance, you were talking about in your presentation that because of the subduction along South America, there might be some water release which may change the melting point, etc. Maybe attenuation becomes important that you may need to address, etc. So you need to take better physics in the inverse problem as well, right?
Mm-hmm.
But how can you? Yeah. Sure.
He's already back.
Okay. By the way, how many questions should I ask? Or is there a time limit? Because otherwise I can discuss with Caio forever.
I think it's half a
We have 4 hours for the discussion, so
Oh,
about
dear.
1 hour for each member. I don't know.
Oh dear. Okay.
But in the end, all the questions are the same, so maybe you can cut a bit.
Okay, sure.
Okay.
I don't want to keep everyone here forever either.
Jordi, você está nos escutando?
Yes, yes.
Okay. Thank
Okay.
you.
So as I said, I'm not planning to take all your time. So probably one last one or two questions. So Caio, I knew that you rewrote some of the routines yourself to perform adjoint tomography. What was your motivation to write your own routines rather than using some existing tools? And what is the advantage of your own routines compared to existing ones?
So whenever I'm using a computer code, any kind of code, I want to understand this code as much as I can. So I want to gain a deep insight in the code. For instance, SpecFan 3D Globe. Of course, I would never try to write a code like that. I would take my entire life and I wouldn't get even closer. But during my undergrad, I implemented a 1D Spectral-Element method. And this 1D implementation gave me an excellent insight in the overall features of the method. So when I started working with SpecFan, I knew very well. Of course, I don't understand everything. I don't understand how self-gravitation is implemented, for instance, not the details, but overall, I understand the method very well. So when you have a problem, if you understand what you are doing, you can solve the problem, you can address that problem. When I started using the routines for window selection, for instance, and first of all, I wanted to incorporate the workflow. So I wanted to, for instance, use a single script or maybe just 2 scripts to create the joints, make the selections, create the joint source, make the figures. First, I was trying the FlexWing package, the actual FlexWing package within Fortran. Then I found PyFlex, which is great. And my first tests were done using PyFlex. But I was intrigued about the configuration parameters because there were many configuration parameters. I read all the documentation, but still there are some details I were not understanding. Sometimes I tried to change the parameters to achieve a result, and I was not achieving that result. And that made me wonder, okay, perhaps I have to implement this by myself, because if I make my own implementation, then I will know how things are working in the first place. So I don't have to use my implementation. I could just make an implementation, understand what's going on, and then switching back to PyFlex if I think PyFlex was better. But during my implementation, I found your paper from 2011 showing the instantaneous phase measurement. And I wanted to use that measurement because I saw that, in my opinion, there was some advantages over the multi-taper or just cross-correlation measurements. And so I designed my codes from the beginning to work with instantaneous phase measurements. So from the beginning, I wanted to select large windows because I knew large windows were better. Another thing I wanted to do is to implement a separated stage in the algorithm just to get rid of the noise component, because FlexWin tries to make the selection all at once. It gets our data and tries to select the windows straight away. But if you could clean your data before, you can relax some of the constraints in the windows, and you can select larger windows or maybe even more windows. So in the end, I wrote my routines, and I liked the result. I liked how the windows were behaving. I remember that you gave me some suggestions because I had some small windows at the tail of the seismograms. I removed those windows, and after some fine-tuning, the results seemed robust. So I just stick with my codes and didn't use the PyFlex or the PyAdjoint anymore.
Okay, that's fair enough. But there is a heavy workflow to perform these iterative inversions, right?
Mm-hmm.
From data processing, computation to measurements, computation of adjoint sources, forward simulations, adjoint simulations, model updates, blind search, these and that. So what do you think where you should try to improve this workflow? Or what is the bottleneck in your current workflow and how it can be improved? Or do you see what kind of opportunities to further improve?
Mm-hmm. Well, there are several things I want to improve. One of the things is implemented another adjoint source, because right now I only have exponentiated phase. I want to implement the envelope measurements, waveform measurements. And there's a bottleneck because right now I am downloading the seismograms from the cluster, the syntactic seismograms from the clusters, and running the window selection. Of course, you don't have to run the window selection every iteration, just a few iterations, but I am running the adjoint source computation on my computer, and then I'm sending the data back to the cluster. The reason I was doing that is just because I wanted to have more control. I wanted to check the windows carefully, but certainly a great advantage would be incorporating ASDF into my routines. So I don't want to use these ASC files anymore for the adjoint source. I was not creating ASC files, I was saving some binary files, and I have another routine to expand those binary files. I can save some time, but still is a bit cumbersome solution, and ASDF is much cleaner. So I wanted to implement ASDF. I wanted to implement more adjoint sources and make my routines work on the cluster itself. So that would be a great improvement for the workflow, certainly.
So do you think that if you can move everything to a cluster or supercomputer, most of your problems will be solved?
It will be easier because if you have everything in the cluster, you don't have this need to download the data, send the data back. This creates some bottlenecks in the workflow. It's cumbersome, so it's better to have everything in the cluster. So yes, I think it would be more productive if I had everything on the cluster.
Yeah, well, I agree with it, but I have bad news. That may not solve all your problems, and it may create additional other problems. And we can discuss then how to improve those workflow challenges once you move everything to a supercomputer. One last question, Caio. What are you planning to do from now on in terms of research?
Okay, so
what would you like to work on, or where you would like to carry your research?
one topic I really want to study, as I told you, is normal modes. So I think normal modes are awesome because they are such a beautiful solution for the wave equation. So I definitely want to study normal modes eventually. There, of course, there are many other topics in seismology I am interested in. I am interested in source inversion because I have been doing forward modeling and structural inversions in the last 5 years. And at this point, of course, I'm not saying that, okay, I know everything, I don't have anything else to learn. Of course, this is obviously not true. I have a lot to learn yet. But I see other areas of seismology in which I have very little knowledge. And normal modes is one of these areas. And I do want to learn normal modes.
So is it more a theoretical interest? Because yes, there's a beautiful mathematics behind normal modes. Or do you also have some scientific problems to address with normal modes about Earth's interior?
Both of them. I think in the first place, I have to understand the theory very well. Because after I understand the theory, then I will know what can be achieved using normal mode simulations. But about the Earth, I want to study the core, the Earth's core. I think the Earth's core is also very interesting, and perhaps I could use normal modes in the core. I'm not sure about that, but yeah. So scientifically speaking, I want to look into the core as well.
Okay. Thank you, Caio. I think my questions are... I can continue, but I think that would be enough.
Okay. Thank you, Ebru. Thank you. So next, Julia, can you do the questions now? You are muted.
Yeah, sorry. First of all, congratulations for your work. I think it's quite impressive.
Thank you.
Very impressed about the amount of work that you did for a single thesis, right? That's a bit unusual in a good sense. So congratulations on that. Okay, so my questions will be mostly about your paper on the adjoint tomography. Okay, but before we go into that, let me say something about the other paper, the one that you submitted to the European Journal of Physics. Is that the name? On the sensitivity kernels?
Yes, not yet. I didn't submit it yet. It's about to be submitted.
Well, I really enjoyed reading that paper. Let me tell you that. I mean, it's exactly the kind of material that I would like to use in my classes for teaching what finite frequency propagation is about to the students, right?
Great.
So my question here is, I mean, if I understood it correctly, you are approximating those finite frequency kernels by using a single surface that separates source and receiver equally, right? And then integrating for all possible paths that kind of refract across that boundary.
Yes.
And to get the full story, you should do that integration, perform that integration of all possible planes and all possible paths. And yet, you know, by doing that, you recover the essential behavior of finite frequency, which is that hollow banana donut kernel for travel times and all that. Why do you think that, you know, just a single surface suffices to get those effects? Because my guess would be that, you know, that's an effect from multiple interference from many ray paths, and with a much smaller subset, you are getting the essence of the finite frequency. Why do you think that is possible? I mean, how, or in other words, how did you come up with the idea that, you know, by using a single surface that would be enough?
Well, that's an interesting question. I have been thinking about that for quite a long time. So if you really want to make sure that your paths are canceling each other out, you should take into account all possible paths, given the craziest paths.
Yeah.
But since I knew that we know the theory for finite frequency, of course, I didn't have a good understanding of the theory. So, but we know from the actual theory, the more formal theory, that those other craziest paths, they just cancel each other out. It doesn't matter. So because we know these crazier paths doesn't matter, if I make a simplified model, if I create a simplified model in which I'm trying just to take into account the paths which roughly approximate the Fresnel zones, I think I should recover the basic properties of the kernels themselves. That was my first guess. And as I explained it in the paper, those kernels, they have some nice properties. So for instance, we know that the width of the kernels, they change with the square root of the wavelength and also the distance between the source and the receiver. This is a behavior which mimics the actual kernel, so it's a good sign that our model is representative. We find a hollow travel time kernel, which is what we wanted in the first place. So yes, I know that it's not a very formal proof that my model is representative, but my main goal was just to understand what was going on. So just to get a feeling of what was going on in this problem. And that paper was tricky because in the beginning, I tried to compute the kernels in 2 dimensions because I thought, okay, in 1 dimension, you don't have anything interesting at all. You don't have a kernel, you have just a line. But in 2 dimensions, you should have these effects in the first place. But eventually, I found that 2D wave propagation can be even harder than 3D wave propagation, because the green function is more complex, because the Huygens principle does not apply anymore. So in the end, I switched it to 3 dimensions. So I tried to keep as simple as I could and still reasonably representative of the actual kernels.
Right. No, I mean, I think that you succeeded with, illustrating those effects. So let's move to the paper, right? Which is where I have most of my questions. So, okay, one of the first things that it kind of caught my attention is that, you spend the beginning of your thesis talking about full waveform inversion. And when you start section 3 in page 10, you say that you exclude the amplitude information and you keep only the phase information. Right? So you're basically dumping all information on amplitude and sticking to the phase.
Yes.
Why?
Well,
because if my point is the following: if you use only the phase, I mean, that's basically what we do when we pick travel times, right?
Not really.
Information. So exactly. So that's what I want you to explain to me.
Yes. Okay. So first, why I dumped the amplitude information? Because most of the nonlinearity of the inverse problem comes from the amplitude information. So your objective function using only phase information is already very complex. In my slides, I showed a 1D objective function, but the objective function for these adjoint tomographies, they have hundreds of millions of dimensions.
Can you project again your slides, please?
Sorry?
Can you project again your slides?
Yes, of course. So, just give me a second. Okay, I'll start sharing my screen again. Okay, can you see it?
Yes.
Okay, let's. Yeah, that's the figure I was talking about. This is a 1D objective function, but in reality, our objective function has hundreds of millions of dimensions. So it's an unimaginably complex structure. And if you introduce amplitude information, it gets even more complex because you are introducing a lot of nonlinear behavior into your inversion. Another issue with amplitudes is that you have to be very sure of the data you are using. Because, for instance, if your station was deployed over a soft terrain, for instance, over sand, it shouldn't, but if it was for some reason, then you will have a very local effect in the amplitude. But this effect, unless you have a very high frequency simulation, unless you are doing only a local study, you cannot properly model these structures. So you are introducing some features in your data that you cannot actually explain with your synthetic simulations. So that's another problem. But of course, ideally, we want to use all the information in the seismogram. That's what we want. But without using amplitude information, the problem is hard enough. That's the point. When you dump the amplitude information, you don't retrieve an usual travel time tomography. I mean, a travel time tomography, of course, there are several different methods, but if you are using rate theory, for instance, you are not taking into account the finite frequency effects. We are taking into account the finite frequency effects, and we have very accurate kernels, sensitivity kernels. We are not approximating these kernels. We are computing the actual kernels. Secondly, in a travel time tomography, usually you're only using some phases in your seismogram. Perhaps you are using P and S wave, you may be using PP wave, but in our inversion, each wiggle in the seismogram, each wiggle, at least inside this blue window, each reflection, you can actually use that information. Yeah. So it's like you were doing a travel time tomography using the finite frequency effect and using all wiggles inside your seismograms. So you're using much more information than a usual travel time tomography.
So what would it take to add amplitude information? How should you change your approach to be able to model amplitude?
Okay, so you have to be more careful with the data you are selecting. You certainly have to be more careful about the attenuation, how you are handling attenuation. Right now, I'm not trying to invert attenuation. I have an attenuation model, and I'm just keeping this model the same over the course of the iteration. But attenuation is extremely useful to constrain the amplitude information is extremely useful to constrain your attenuation model. And that's what we are working now. So I'm working with Professor Ebru and a friend of mine in Turkey, and he's doing some attenuation simulations. So we are working on that. Is the next step of this waveform tomography, of these adjoint inversions. So it's a harder problem, but we are looking to that.
That could help you understanding those low velocity anomalies that you have in your velocity model.
I'm sorry, Professor?
That could help you understand the nature of those low velocity zones, the spots that you see in your velocity.
Yes, perhaps.
Model for your region.
Yes, as Professor Ebru said, the better the physics you use, the more, if you are taking into account attenuation, if you are taking into account, for instance, azimuthal anisotropy, because I'm using just transverse anisotropy, transverse isotropy actually, but if you're taking into account the azimuthal anisotropy, then your simulation gets progressively more robust. Of course, that if you have more parameters, you also need more data to constrain those parameters. But if you have that data, then yes, your inversion will certainly improve, or should improve in theory, at least.
So now that you mentioned transverse anisotropy, which that leads me to my next question, because you only show in your paper the results for the vertical shear wave velocity, right?
Yes.
And there are transverse isotropy has 5 parameters, and you don't show absolutely anything about the other 4. Why?
Yes. Well, we have the model for all the other parameters, but usually the most reliable parameters is the vertical S wave, and why not the horizontal S wave? Because usually the vertical S wave can be better constrained using the vertical components of the seismograms. So you have more noise in your horizontal components of the seismograms. So that's one of the problems. But also, for instance, density. Density is harder to constrain. We are not trying to invert density. We are just using a simple relationship between the VS, the isotropic VS, and density as a proxy for density. We are not trying to invert density. The VP is also trickier to invert, so we are not trying to interpret anything. So we are looking into the VS, and also VS has a shorter wavelength. So you should be able to see smaller structures using S-wave. S-wave is also more sensitivity to, for instance, if you have a partial melting in your mantle, the S-wave is much more sensitive than P-wave. So that's why. So just by trying to interpret S-wave, the paper is already very big. So we are not trying
to interpreting the vertical one. If you were, interpreting the horizontal shear wave, I mean, whether you have the regions with positive radial anisotropy and negative radial anisotropy could give you some indication about mantle flow, for instance. Right?
Yes, but only
things like that.
Yes, that's true.
Is the horizontal S wave not reliable at all?
No, I'm not saying it's not reliable at all. I'm just saying that usually it's less reliable than the vertical component. And of course, you can keep working on your study. You can keep adding some further analysis into the study, but eventually you have to stop. There is a time there was a deadline for my PhD. There was a deadline for my defense, and I was working on several papers simultaneously, so I have a limited time. So yes, but many people are making me suggestion, perhaps you could look into this or you could look into that. And yes, we can study even further. We can try to look into other parameters, but I have to stop at some point. And we decided to stop just by trying to interpret the vertical S wave components.
Okay. What else? Yes, in section 3.2, when you talk about forward simulations, there is a sentence that, I found kind of weird. It's in the middle of a paragraph. You say that MoCo is also honored whenever the crustal thickness is less than 15 and more than 35. So what happens when the value falls between these two limits? You just ignore the MoCo?
Which page is that?
Page 13.
14?
13, 1-3.
1-3.
So that's in section 3.2. When you talk about the MoCo.
Well, I think. Okay, you are talking about just the paper. You are looking at the paper numbering. Okay, I'm sorry. I was looking into the numbering.
Page 13 of the chapter. I don't know.
Okay, I'm trying to just give me a second because this PDF is very large. So
it's page 103 in the thesis.
Okay.
Yes.
Yes, I'm almost finding it. Okay, page 13 is section 3.2. 3.2. So which line is?
It's in section 3.2. It's below the 3, 6, the 9th line.
Okay. Yeah, that's a limitation of the method. Working with the crust is super hard. So even by using spectral elements, they can change their shape to honor some different structures, but there is a limitation. Of course, if you distort your spectral element too much, you would run into numerical instabilities, and you could add more spectral element there, but then you would increase your computational cost. So at some point, we have to make some approximations. So the SpecFin creators, they did an amazing job. They put a lot of effort into making accurate simulations, but there is a limitation to what you can do right now. And the crust is very hard to implement. So for instance, the surface topography, we are not using the exact surface topography. For instance, Mount Everest is not at almost 9 kilometers above the ocean level into the spectral mesh. It's something around 6 kilometers, I think, because you have to smooth the surface topography a bit to increase the numerical instability. And when you change, for instance, in South America, we have a challenge because we have the Andes, so a very thick crust, and on the west we have the oceanic plate. So there is a relatively fast transition from a thin crust to a much thicker crust. And in those cases, you have to adjust the mesh. Meshing is super hard. Meshing is the process by which you create the mesh for your model. To run the simulations, you have to create a grid, a mesh to represent your model. And meshing these regions is super tricky. One thing we have done is adding a third layer of spectral elements in South America to improve the accuracy. There was a penalty in computational time, but we did this. We paid this cost to improve our accuracy. But you cannot fully honor the crust thickness. Sometimes you have some problems. And you also, you do as much as you can to avoid a sharp transition, for instance, the Morro discontinuity, crossing inside a spectral element. Because between two spectral elements, you can have a sharp transition. That's okay. The method can handle this. But when your sharp transition enters the spectral element itself, you will have some issues because inside the spectral element, you are trying to fit your model using Lagrange polynomials. And as I explained it in the B-spline section, polynomials doesn't like sharp transitions. They would have some problems. So that's why you have to, you put some constraints into your crustal thickness.
Okay, so it's a difficulty with parameterization of your model. Okay, fair enough. If we move in the same page forward, there is some statement here that, if I were reviewing the paper, I would be concerned. You say, for instance, that the events were selected by checking the waveform similarity between observed and synthetic waveforms. That's, I guess, with respect to the starting model, right? And then later on, you say that we perform a visual inspection to eliminate problematic data. I mean, the way you express it, it kind of gives the impression that you are tampering with the data so that you get a nice answer.
I'm sorry, Professor. Could you repeat?
The way you express, especially this last section, we perform a visual inspection to eliminate problematic data. It gives the impression that you are tampering with your data, that you are removing what you don't like so you get the answer that you want. What do you mean with problematic data?
Well, problematic data. Okay. So theoretically, our algorithm should get rid of all stations with problems. But as an extra care, just to make sure that everything was okay, I checked all stations one by one. I created figures for all waveforms, comparing all waveforms, and I checked all stations one by one. For instance, there were some stations in which the station orientation was wrong. So there was in the metadata, there was an azimuthal information. So it says, for instance, that the north component of your seismogram should be 30 degrees off, but it wasn't. When you look into the seismogram, you would see some reversed phase, like perhaps someone just switched the two plugs in the seismic station. Okay. And of course, usually those kinds of data would be rejected by the window selection. But sometimes, by chance, you can have some fitting where you should have none. And in those cases, the window selection cannot do, I would say that 95% of the time, it would do the right thing. But there are some limitations. Sometimes you would introduce some problematic data in your inversion, and you don't want this. You could either improve your algorithm or you can check the data by hand. So since I was still developing my routines, I was in the first stage, and I didn't rely on my code very much. I decided to check the data visually, one by one. So I found those problematic stations and I removed them. It's not that you are, okay, this does not agree with...
I can imagine that it wasn't that. I think think that
Yes.
required a better explanation.
Yes, it's not just confirmation bias. So it's just, we know that the data is wrong. We know that there's a serious problem. We cannot use the data in our inversion.
Okay. So let's move forward. You showed in your presentation a slide, it's quite interesting, of the misfit as a function of the number of iterations at several jumps. That one.
Yes.
Right? So you said, for instance, if I recall it correctly, and I think that's written in the paper too, one of those jumps is because you were seeing some high frequency features in the transition zone or in the mantle, and you decided to smooth it out? Or...
No, actually, there is no jump. This transition is over there. So
But there are some jumps here. For instance, in the fifth iteration, you did something to your model that makes the misfit get bigger instead of smaller. And there is another one in iteration 14 to 15.
Okay. What it did, we added a second period band. So before, we were just using data from 40 seconds to 100 seconds. And iteration 15, we added a second period band from 30 seconds to 60 seconds. And that's why the misfit increased.
Okay. So Dr. Ebru asked you about the uncertainties. That's one of the questions I had for you that you already answered. What about the uniqueness of your model? Because I have the impression that, to implement this adjoint method, you kind of have to guide the convergence process and watch it carefully so that it doesn't get into trouble.
Mm-hmm.
Right?
Yes.
At the end, for what I see in the paper, you get a final velocity model that explains better, independent waveforms than other velocity models, right? So you succeed in improving the accuracy. That's my impression. But how would you explore the uniqueness of your velocity model? What do you think? How do you think that could be approached?
Well, I don't see any easy solution for that. The only solution I can think about would be if you have a limitless computational resource and you could run infinitely many simulations to check all the other possible solutions. Maybe there is a better solution for that, but I don't know the solutions. I cannot think into, I cannot find an easy solution for this, for the non-uniqueness.
Okay, let me see. Right. So that's the uncertainty. So let's go to the interpretational side of your tomographic images.
Mm-hmm.
So you showed in your presentation a slide with 3 cross sections across South America, focusing on the subducted slot.
That one?
That one, exactly.
Mm-hmm.
So, for instance, in the bottom one, the H line, I have a hard time seeing the continuity of the subducting slot. It seems to me that it's more like broken rather than a continuous feature. So could that be a possibility? The slot detached?
Yes, perhaps, but I'm a bit reluctant to make those kind of interpretations.
In other words, if I didn't know that this is South America and this is the along the west coast, I would have never guessed there is a subduction plate in there.
Mm-hmm. Yes, that's true. Yes, that's what I said. That I think the major contribution of my model is for the cratons. So we really could constrain the cratons contour very well. For the Nazca's lab, we found some interesting results, confirming some previous findings, sometimes, other times diverging from them. But yes, we were trying to interpret what we see, but I am not very confident to make such kind of interpretation that say, okay, this lab is detached here or there.
The same comment applies to the Paranaplum, which is in the section right above F2 line.
Yes.
I just see a continuous vertical anomaly. It's 2 blobs one in the transition zone, one in the asthenosphere above.
Yes, that's also, there's a problem with our, it's not really a problem, it is a choice. Our starting model didn't try to keep a continuity between the mental transitions. For instance, S40RTS, which is another global model, I think they imposed a model continuity along the transition zones. But our S3620 didn't. The reason I chose S3620 in 2016 to begin my tomography was that it presented the best fitting with my observed waveforms. So I carried out many forward runs, benchmarking several models, and I found that S3620 was the best fitting for South America. S40RTS, there was another problem with S40RTS in South America, that I could not see a good correlation with the geological structures. In S20 RTS, we see the Amazonian Craton and the San Francisco Craton. Of course, it's a very long wavelength information, but the structures are there. But in S40 RTS, there was not such a good correlation. And those days, I have no idea of these continuity questions. So that's why I stick with the S3620. And that, in the end, that introduced some sharp transitions in our model. It's another problem that we have. But yes, there is no, we see that there are those low velocity anomalies, but they are not so clear as they are in, for instance, the Rodriguez inversion, as clear as the Rodriguez inversion.
Okay, and just one last question. Okay, one of the things that you target in your interpretation is the LAD, right?
Yes.
Have you ever heard of something called the MLD, the mid-lithospheric discontinuity?
No, never.
Okay, you should. Okay, because it has been proposed, not that recently, that discontinuity that you interpret as the LAD, especially in the cratons, is not the LAD. It's an intralithospheric discontinuity that separates an old craton from a younger cratonic root that was added later on. Okay, so I wouldn't be so confident that there is a discontinuity. Sure, there might be, right? And it matches what you see with the SRFs. That's not necessarily the LAD. It could be that mid-lithospheric discontinuity. It's impossible, right? So that's basically it about my questions. So, Carlos.
Thank you, Jordi, for your questions, for your contribution. So now we can have Daniel. Thank you, Daniel.
Yeah.
Questions.
Yeah. Thanks. I'll also start out by just saying it really was great work. It was great to listen to your presentation and to look at your thesis. It's a pretty impressive body of work that you did. It's very familiar to me because it seems like you did basically everything I did for my thesis, but with a much harder and much more difficult methodology. So I'm really impressed.
Thank you.
So yeah, a lot of the questions I had, some of them have been asked. So hopefully I'll be able to keep this relatively brief. But I guess most of my questions that I have are really about how to understand your model in the context of all of the other models that we have in South America. And so I'll get to that in a second, but I just had one quick technical question that I didn't understand about your the methodology. You've talked a little bit about how you invert for density as one of the parameters, and I know that's not one of the parameters you talk about in the results, but you talk about how there's a direct scaling that you use. Is that right?
Yes.
To get to density.
Yes.
So I'm curious about you mentioned in your interpretations when you're trying to interpret the cratons, you explicitly say how some of what some of the change in amplitude of the cratonic material may be a result of a different densities with respect to velocity. And so you sort of explicitly state that there's not a linear relationship between density and velocity. And so I'm wondering if that assumption that I guess I'm just curious how that assumption that you make affects your results, or if it does at all, and yeah, what the implications might be of that.
Mm-hmm. Okay, so this is the relationship we are using to approximate density, and as all of the other parameters, as azimuthal anisotropy, as attenuation, the more, of course, the less constraints you insert into your model, the better. But the truth is that density is very hard to constrain, especially in these period bands we are working with. So we know that this approximation does not hold everywhere. So it cannot simultaneously hold, for instance, inside the cratons and in the mantle wedge, for instance. But still, we believe it's better than trying to constrain a parameter that we cannot really constrain. So yes, certainly by making that assumption, we are introducing some sort of systematic error in our inversion, and we have to be aware of that. There are always limitations to what we do. The reason we are we are suggesting that there may be a compositional change is, for instance, for the Amazonian craton, we know that the thermal anomaly alone cannot fully explain the difference in velocities. So it cannot be just temperature change. So it has to be something else. So the next thing we can think about is composition. So iron depletion would change this. But yes, that's the point. There is a limitation. We are introducing some kind of bias in the model, but it's better than trying to invert density, because we cannot invert density yet.
So in the case of the cratons, where you have this faster velocities that are also more buoyant or lower density, what is the systematic bias? What does that look like in the results? Or what would you speculate? I know you can't invert for it, but what would you speculate? Like what direction that would take? Are these velocities, given that assumption, are the velocities that we're seeing faster than they would be if we were accounting for those density variations, or slower than they would be?
Yes, I have to think a lot about that before answering your question. Of course, if you are fixing one of the parameters, then you have to change the others to explain this. But if that would increase or decrease your velocity, I have to change more about that before answering. One thing I know is that the amplitudes in my model, the velocity anomaly amplitudes, they are large. They are at 110 kilometers. We were observing 11% velocity anomalies. So they are on the edge of the anomalies you can explain using only temperature change, for instance. So perhaps, yes, maybe they are increasing the velocities inside the cratons, but I cannot be sure of that answer.
Okay, yeah, thanks. I didn't know if I don't know the answer, so I was just really curious if there was an easy answer to that. So yeah, mentioning the amplitudes brings me to another one of my questions. I think about this more in terms of the slab, and I'll get to that in a bit. But there's a lot of amplitude variation in your model in different structures. So in the cratons and in the slab, and I'm curious how well constrained you think these variations are, and what we should take away from those amplitude variations.
Yes, I would say that for the cratons, these amplitude value, maybe not the absolute value of the amplitude, but at least the amplitude changes inside the cratons are reliable. That's my feeling. Based also on the point spread function test, I know that I have enough resolution at this depth and at this region to resolve those structures. So yes, I would say that at least in the cratons, the shape of the cratons are reliable. And they also agree very well with the geology. So yes, I think they are reliable.
So the shapes are reliable, but not necessarily, and the relative variations in amplitude are reliable, but not the absolute amplitudes.
Yes, not necessarily the absolute amplitudes.
And so what about in the slab?
The slab is certainly less reliable, and the deeper you go, the worse it gets. And so, but yes, but at least in the upper mantle, I think this slab is relatively reliable in the transition zone as well. But you still have some horizontal smearing, so you have to be careful in your interpretations of the slab. But yes, about the amplitudes, I have the same statement. So the absolute amplitude, I don't think they are very reliable, but the relative amplitude, they should be relatively reliable also in the slab, at least for the upper mantle and the transition zone. Not very much in the lower mantle, because our ray coverage in the lower mantle is much lower. It decreases sharply in the lower mantle.
So what are the implications of that? If I mean, there's parts of your slab that are varying pretty significantly in terms of amplitude, and if we can rely on these relative variations, like for example, the amplitude at the equator is very different than the amplitude around the Pompeian flat slab. What does that tell us?
Well, since you are trying to interpret only the relative change, well, this, for instance, there is a weakening in the amplitude here at the equator, but it's almost the size of our resolution. So I wouldn't try to interpret this, but certainly there is a difference here. And for instance, the amplitude seems stronger in the southern portion of South America and weaker in the northern portion of South America. But we also know that this region of the slab is older, so it should also be cooler. So this relative amplitude makes sense. So if you think this slab is cooler than that slab, so you have a good explanation for these velocity changes.
Okay, so they could be an age relationship for
yes.
the slab entering the trench. Yeah, that certainly I see that in the central latitudes. That's a little bit harder down in southern South America, where you're pretty close to the it's pretty young down south of 30 degrees.
Yeah.
But yeah, that's helpful. So yeah, I guess, and this is a similar question to what Jordi asked, but this is those amplitude variations, at least as we get deeper, it seems that the slab is a bit broken up. And especially compared to some of the other models that you compare to in the paper. And I'm wondering, you mentioned before that it's maybe especially at the transition zone discontinuities that's not believable, but that's true even in the map view slices. So if we look continuously along strike, and I'm curious, do we think is the reason to believe the slab is breaking up is the reason why I might trust these gaps in the slab relative to some of the other tomography models that have a continuous slab? Or how should I approach thinking about the sort of globular nature of the slab?
Well, since we are not observing these features in the previous models, and since we know from the resolution tests that there are some horizontal smearing, I would be very careful trying to interpret this as some kind of slab detachment. It could just be an artifact from the inversion. So simply, I cannot make such a statement. I cannot say, okay, this lab is detached here, for instance. It could just be the numerical smearing. If there were other models showing the same gaps in this lab, then I would be more confident of making such a statement. But no, yes.
So do you have a sense of why, with the technique that you used compared to some of these other tomography techniques, that we might see gaps in the slab here that we don't see in those other techniques?
Well, for instance, for the cratons, I know that I have a high resolution. So for the cratons, I am confident to make that, because we have a more complex method, for instance, maybe we get a better resolution and we can see some those globular structures better. But for this lab, so I think the major limitation, as I explained during my presentation, is that I am not using core phases because I only have a regional simulation. I'm using a single chunk, so I don't have core phases and I don't have rays crossing from below. So I think that's the major explanation for the horizontal smearing. My first guess, the first time I saw these elongated structures, I was thinking about the smoothing, because we use a larger smoothing in the horizontal direction, but still the size of the smoothing kernel was much smaller than the amount of smearing we were observing. So this is not an explanation. So my advisor said that, I was talking to my advisor, and we think that most likely this is related to ray coverage, the fact that we only have horizontal kernels, mostly horizontal kernels here. So if I had more computational power, I could have done a global tomography, and I'm very confident that this lab would be better constrained. And am I saying that because in the paper, I also showed GLAD M25. And as I mentioned, in the long wavelength, my model is very similar to GLAD M25. And the GLAD M25 does not show these globular structures that much. Yeah, well, it still shows some globular structures, but there is, for instance, if you look into this profile B prime, it's clear that there is a much better continuity in GLAD M25 than there is in my model. And there is a very elongated structure in the transition zone. And this structure is not on GLAD M25, so we don't see this level. So perhaps perhaps I am seeing more details than other models, but I won't make such a statement because I'm not very confident of interpreting these structures for the reason I mentioned. So I think if I have a global simulation, I could those elongated structures, I most likely would disappear, and perhaps I would have less globular structures inside this lab.
Okay, cool. Yeah, that's helpful. I guess I just have one more quick question about resolution. So these the sensitivity kernels that you use, they're pretty broad. They're fully accounted for, and so they cover a much wider region than the ray. The point spread functions that you use to look at resolution, I'm not totally familiar with them, but they're independent. They seem to be independent of the surrounding structure. And since our sensitivity kernels cover a much wider region, that indicates that whatever the velocity model is surrounding these point spread functions, not just what is at that locality, should affect resolution in other parts of the model. So having a slab in there, for example, any of your sensitivity kernels that cross that slab's going to affect your resolution in other parts of the model. And so I'm curious about how to, this is something that we typically do with recovery tests, right? I understand that's not something that you can do with the full waveform inversion, but I'm curious about how I should think about resolution in the context of the nonlinearity with other structures. Did that question make sense?
Not sure if I understood your question. I'm sorry.
Let me try to rephrase. So when I think about a recovery test, a synthetic anomaly recovery test with a body wave tomography, I can make my input structure just a delta function, right? And
Yes.
that'll tell me some information about the resolution, about what structures can be resolved. But the recovery of that delta function will be different if there's no other structure in the model versus if there are other structures surrounding that delta function.
Mm-hmm.
And that's not something that you're able to do with the full waveform inversion, I understand, because you can't do it's too expensive to do detailed synthetic modeling. And so I'm curious about how you think how I should think about those point spread functions in relation to the fact that you don't have that external structure in these resolution tests. How do I get that information for the full waveform inversion that I can't get from the synthetic test that I would do for body wave tomography?
Mm-hmm. Yes, I'm thinking about that. I didn't spend too much time trying to understand the theory behind the point spread functions. As far as I know, they are just trying to estimate the Hessian curvature at this region, because in the full waveform inversion, we cannot use the actual Hessian function. So we don't have access to the full Hessian matrix because it's too expensive and it's too large. So we only use the diagonal of the Hessian matrix, which we actually in approximation to the diagonal of the Hessian matrix, which is the pseudo-Hessian. So the pseudo-Hessian more or less show your ray coverage. But in this point spread functions test, they are just trying to show the Hessian curvature in the region. And I think this is related to one of the figures in my thesis in the beginning, when I was talking about geophysical inversion, that I showed the difference between a well-constrained model in which you have when you move away from the minimum of your model, your misfit increases very quickly. But if you have a more ambiguous solution, then you can change your model and your misfit changes very little. So I think the point spread function is mostly trying to capture this effect. So about the effects of anything around, I'm not so sure, because it looks to me like it's only measuring the point resolution, the resolution at that spot. It's not taking into account the effect of other structures in the model. Just to give you, it just gives you any, and actually even the point spread functions, they are relatively expensive because for each point spread function, we need a simulation, a different simulation. So even those point spread functions, they are expensive. So what you do is usually you look into the region of your model with the best ray coverage. For instance, in my case, it was in the middle of the Parana Basin, and you compute the point spread function over there. And you also look into the worst region of your model, the region in which you expect to see no resolution at all. And those two will put some boundary constraints in the minimum resolution you can recover and the maximum resolution you can recover. In my case, I also carried out more tests in the middle of the NASCA's lab because I wanted to have an idea of the NASCA's lab resolution, but I think that's it. That's everything you can get from these point spread functions. Maybe I'm wrong because, as I said, I didn't go into the theory very deeply. Maybe you can say more about that, but that's my understanding right now.
Yeah, thanks. I'm still trying to understand these point spread functions as well. So just a quick follow up on that. You say that you keep mentioning the resolution of at that location, for example. And can you tell me? Can you just clarify to me what you mean by that? Do you mean the amplitude recovery, or do you mean the size of an anomaly that you can recover, the dimension, the like sharpness of boundaries that you can recover? What do you mean by resolution?
Mostly is the minimum size you can recover. Mostly is that what I'm talking about. So what is the shortest wavelength we are really confident that we can resolve? So for instance, I know that my cratons, they can be resolved. The cratonic nuclei, they are more or less the size of these. They are actually a bit larger than this point spread function. So I know that I have resolution to resolve this size of cratonic nuclei. But yes, it's mostly about the minimum wavelength you can resolve.
Great. Great, thanks. So I'm just going to move on to one or two quick questions about interpretations. One of the aspects that you talked about in the paper was about where the slab does and doesn't go into the mantle, the lower mantle. And I'm curious about your perspective on why we care about what the slab does in the lower mantle. What does that, what do we get out of, what do we get, especially in South America, but what do we get out of knowing where the slab does and does not go into the lower mantle?
Mm-hmm. Yes, I think this is an interesting topic. I know that some decades ago, people thought that the upper mantle and the lower mantle, they have separated dynamics. They were not being mixed with each other. And now we know that this slab can penetrate into the lower mantle, but there are some interesting interactions at transition at these seismic discontinuities. So, for instance, if the mineral phase change is exothermic or endothermic, that changes if the slab will be how can I say that? I know that depending on the kind of phase transformation, this can facilitate or this can hamper the slab penetration into the lower mantle. So this is something I think is very interesting to know about. Some speculation is also about the composition of the D double prime layer. So some people think that the D double prime is like a kind of slab graveyard. So knowing that where the slab is penetrating to the lower mantle can also have some implications for the interpretation of the D double prime. So yes, I see mainly those possible outcomes from knowing where the slab is penetrating and where is not.
All right, yeah, thanks. I'll just point out, this isn't really a question, but one of the reasons that I'm really interested in it, and I think a lot of the geologists is this idea that's been talked about a lot recently of slab anchoring in the lower mantle, and that controlling shortening in the upper plate and controlling the timing for uplift of the Andes, and explaining why the different heights of the Andes and the different degrees of shortening along strike. And so I don't think we have I'm still not confident in our models of where the slab does and doesn't go into the lower mantle. So that's why I'm thinking about it, but it might be something to look into as you're thinking about the lower mantle, the slab going into the lower mantle. Well, that's all I have. I'm happy to pass it on. Thanks.
Thank you.
Okay, thank you, Daniel. Thank you.
By the way, I will turn on the lights on my room because I think it's very dark now.
Okay.
Okay.
Ready?
Yes.
Okay. So Bianchi, thank you.
Thank you, everyone. Thank you, Caio, for the opportunity. And I have followed most of your work until now. It was a great time for me to learn a lot from your reports over the work. And also it was I was very happy to see the final results that you got, and everything for me was really amazing, like to see everything that you did. Like it's a great work after everything. And for me, it feels like very complete work in terms that you develop a work and you bring the understanding of the concepts and also presents results with some initial discussions. I'm pretty sure that it will take a long time for us to understand all the features of your work and all the points that the colleagues pointed out about the interpretations. And I will try to bring some points here that I selected, something that I think I could try to contribute a little. I'm not a really expert on this new field of adjoint tomography and FWI. Actually, I'm a little bit far away from tomography. But anyhow, it was really interesting. Like it was really interesting and also instructive to me to read your report. After all, and it feels to me that you had a very hard time to put together everything that you did, because you touched many aspects of theoretical to really practical points, and putting this together should have been a pretty hard time.
Yes.
So the first thing I would like to ask you a little bit, it's about the Misfit Evolution. This picture that you bring about the Misfit Evolution.
Mm-hmm.
And while I was reading the report and I was reading your explanations about the jumps, it came to my mind that every time you move windows or add windows, you are actually changing a lot your Misfit function somehow. You are creating local minima or local maxima somehow. And do you think that, like, and it's further, like when you add windows or you remove windows, you are really changing geometrical aspects of your inversion. And what do you guarantee that adding more window doesn't take you to an inversion path that is not the inversion path that you were going to? Can you measure somehow that you deviated from the direction that you were going when you add windows?
Well, I believe we are deviating from the initial direction, but I think that's the goal, because as I said, avoiding the local minima is one of our main concerns when using this kind of gradient optimization or any kind of Newton-like method. And as I said, there are several ways we can try to avoid the local minimum. One of these ways is using only phase information in the adjoint source. Another way is the multi-stage approach. We first begin with the long wavelength information. But also, our windows are important into this, because first we try only to fit the regions of the seismogram, the sections of the seismogram, in which we are close enough to the local minimum for that objective function. So we are more confident that we would not end up trapped into a local minimum. And once we reach that local minimum, we try to enlarge our windows. And by doing that, we are changing our objective function. We are changing the direction we are following. But hopefully, we are now following a direction that points towards a more representative model. So in the end, we want to explain as much as we can from our real signal. As I mentioned, we cannot use in the entire time series, obviously, for there are limitations, but as much data as we can include, we always try to include. So ideally, at the last iteration, we would have only a single window for our entire seismogram. Right now, we cannot do this yet for the reasons I have explained. But if you can enlarge our windows, that would be great. But what I realized is that after this first from stage 1 to stage 2, I recomputed the windows. I managed to insert, I think it was 5% increase in the windows length, or 10%, I don't remember exactly. It significantly enlarged the windows. But after that, I tried to recompute the windows again, and it didn't change anymore. So somehow I reached the limit of the usable data I could include in my inversion.
Okay, and then you just create the drop there when you included more frequencies.
Yes, because
at iteration 6 to 7, or yeah, 6 to 7.
6.
Yeah, the drop from the
the drop. Yes, that's because this is a bit hard to understand. I tried to normalize the windows because I didn't want that the size of the windows were affecting my misfit. I wanted that my misfit were only dependent on the waveform similarity. So if that was the case, we should see an increase in the misfit here, because we are decreasing the minimum period. So we are increasing the waveform complexity. We are making the data harder to explain. But my attempt to normalize was flawed, because this relationship between the windows length and the misfit is nonlinear. So just because you double the length of your window, it doesn't mean your misfit would double, because you are adding data that was not previously included in your inversion, and it wasn't previously included in the inversion because it was too different to be included. So this relationship is nonlinear. So I didn't find a nice way to eliminate the window effect, to make this figure easier to interpret. So I decided just to keep the way it was without any normalization. And there is this trade-off. You increase the frequency content, your data becomes more, the discrepancy in your data increases, but that decreases the amount of selected windows, which in the end decreases the misfit. So that's why we have these jumps. But the most important feature is that inside each of these stages, so during the time in which you are keeping the windows fixed, you are observing a misfit reduction. So we don't try to interpret the transition from one stage to the other. We just try to interpret, we look into each of these stages, and we see that the misfit is decreasing. And we also know that the overall misfit decreased by 50%. And how do I know that? Because after I finished the tomography, I used the same windows I have used for the last iteration, for the first iteration. So I run a high resolution simulation with S360 down to 70 degrees, down to 17 seconds, I'm sorry. And using exactly the same windows, you can have a fair comparison between your starting model and your final model. So, and we know that overall, there was a misfit drop of 50%.
Okay, yeah, really, by reading your thesis, I was very happy to see how you validate your results in the end, because like the FWI imposes a lot of difficulties in testing the final model, especially evaluating the resolution. As Daniel pointed out a little bit, we are much more experienced when we are working on other types of tomography to do those tests that you are more or less confident to interpret and understand, but here is difference. Also, moving on, like one thing that I didn't really understand too much is the term that you use is cross-correlation travel time residual, and it has to do with those histograms in the end. Like, can you explain to me what is this cross-correlation travel time residual?
Yes, of course. Let me go back to the time windows first. Okay, so here we are using those very large windows to make our exponentiated phase measurements. And since we are using the Hilbert transform, it's better to have large windows. We don't want very small windows to make those measurements. So, but I wanted an independent measurement. And cross-correlation, and cross-correlation is meaningful when you have a small section of your seismogram, when you have, for instance, one cycle or perhaps two cycles of your seismograms. So to make those cross-correlation measurements, we split these large windows into several smaller windows between 1 and 2 period cycles. And for each of these smaller windows, we can carry out a cross correlation. So we slide the two traces relatively to one another, and we measure the time difference between them. And by doing that, we can assess our residual with more detail than the Misfit function is providing. Because now we can see that, okay, for some, so each data in this histogram is actually a single wavelet that was shifted relatively to the synthetic seismogram. So for some of the data, we have lower than expected travel times. For other measurements, we have higher than expected travel times. But what we do know is that in the end, after our 23 iterations, our dispersion decreased. So our histograms are narrower. If our model was perfect, we will have just a spike at 0. But the fact that the histograms are narrower now means that you decreased your the misfit between your observed and the synthetic data. And we evaluated this using a different measurement. So we are using an independent data set, a data set that was not included in the inversion, and a different method. It's a much more robust measurement of the evolution of your model after these 53 iterations. And it also shows the bias. There was a reduction in bias. There was a bias before, and we see that the model is shifted towards lower than expected travel times, and after this iteration, the model is much more symmetrical.
Yeah.
Did I answer your question?
Yeah, you answer. Like in the end, you are doing cross correlation in individual windows, but not measuring the cross correlation, but the amount of shifts you need to get the maximum correlation in the window.
Yes, we are using cross correlation to measure the time shift.
Time difference. Yeah, exactly. That is much more related to the phase somehow.
Yes.
To the difference of phase, that is your objective functions. And then, like, one thing that you didn't write in the text is that catches up my attention here in this figure that you show, is that the original histograms were not symmetric. They had a kurtosis somehow, or they are spreaded for negative times. And then after all, you corrected more the negatives than the positives. If you look to the green ones in the middle, and you look to the positive delta T's, they are much more similar the before and after than the negative sides. What's the explanation for that? I mean, you don't compact the histograms, but you compact one side of the histograms, just the negative sides.
Mm-hmm.
This is something that after looking at this for the second time, I realized that, and of course, this is more critical for the longer wavelengths, for the 30 to 60 and 40 to 100s. Like most of the time, you don't fit the large delta T's, but you squeeze on the negative ones.
Mm-hmm. Yes, I think that since the histogram is asymmetrical before the 23 iterations, we still can say that there was a reduction in the dispersion. So the histogram
the reduction is there, but the question, this is something it's just caught my attention, and since you didn't read and you didn't wrote anything on the text, it's just something that maybe it should be important to understand somehow.
Mm-hmm.
Could it be related because we are mostly on a stable area, and we normally have smaller travel times than expected, or predicted by global models somehow?
Mm-hmm.
Yeah,
I remember that I was talking to Professor Ebru about this bias. The same bias is also observed in GLADM 15 and GLADM 25. I mean, the bias is not in GLADM 15 and GLADM 25. It was in S3620, and both GLADM 15 and GLADM 25 has removed this bias. And I think she mentioned that this was mostly caused by the oceans, but I'm not sure, and I don't want to claim a wrong information in her name, but I think that was the explanation. The signal, about the signal being negative or positive, of course, depends on the convention you are using. And actually, I know that I'm using a different convention from the GLAD papers, because in the GLAD papers, the shift is mostly to the positive values. But this is just the sign convention. If you are making your observed minus synthetic or your synthetic minus observed, but in the end, what's matter is that you are reducing the bias and the dispersion.
Interesting, and of course the results are really good because you are reach the symmetrical one. And then moving on to the Caribbean figure, that's one of the points I mostly disagree with you on your thesis. Yeah, that figure.
This figure?
Yeah, like you explain the lack of fit to the Caribbean stations due to the complex structure.
Yes.
But couldn't it be because they are more noisier, Caio? Because they are oceanic stations are surrounded by ocean? Normally those stations have poor signal to noise ratio somehow.
Yes, you are correct. That makes a lot of sense. But in the Central America region, there were stations. There were stations in this region as well. And I have to remove those stations because they were even worse than Caribbean. And this is the stations were, some stations were very far away from the oceans. And we also have some stations in those islands, and they have a much better fitting than the Caribbean. So that's why I believe is more related to the complexity of the region than to just the seismic noise from the oceans.
Okay, so you think it's more related to the complex structure that you have than to the, but the I'm not totally convinced about that, because I know that many of those stations probably have noise data and bad response.
So, yes, in the Central America region, I remember that I was observing seismograms in which the observed data was systematically smaller. I mean, smaller amplitude than the synthetic data, and to me, it looked like attenuation. It looked like a very strong attenuation in this region, but I was not sure. I just thought, I remember that there was like 3 or 4 networks in this region, and I discarded all of them because all of them have the same problem. If it was just a few stations, then okay, this is a problem with the stations. But when you have the entire networks, then I think it's more likely that this is related to a natural feature in the model. Another reason I discarded those stations, it was because they are very close to the boundary of our model, and we know that despite using absorbing boundary conditions, these absorbing boundary conditions, they are not perfect. We still have some reflections of the boundary. So in the end, and I am not trying to interpret anything in this region, so in the end I decided to remove those stations.
Okay. And also there are 2 red stations in your figure. Like
yes, there are.
And then it doesn't make sense to me, but anyway, bad data is everywhere. So
yes, I don't remember why I didn't remove those 2 stations, but I remember that I looked into them very carefully, and for some reason I decided that I had to keep those stations, but I don't remember that reason.
Yeah. But moving to the interpretation part, like one thing that I missed is really, I think, something that Georgie talked about. You are just interpreting the vertical SOA velocity. Did you try to make any other correlation to results in your group? Like, for example, Bruno's paper about SKS splitting. It wouldn't be interesting to compare your results to the splitting measurements of Bruno, especially the horizontal velocities?
Yes, but to make a proper comparison, I would need the azimuthal anisotropy to really compare with her results. I only have transverse anisotropy, and I'm not sure how can I get, for instance, the mental flow direction from the transverse. And I don't know if it is possible to recover any information from the mental flow direction from the just transverse anisotropy.
Okay, so it wouldn't be really a fair comparison somehow.
Yes, I mean, right now we are, my friend in Turkey, he's working with these azimuthal anisotropy inversions. We are trying precisely right now. I have to implement the exponentiate phase and the envelope measurement into his routines so he can carry out. So now SpecFan can, for a long time, SpecFan was able to compute kernels for all of the 21 elastic model, elastic parameters of the elastic tensor, but no one was doing that because you don't have enough constraints to all those parameters. So usually people was just sticking with transverse anisotropy, but now we can also compute these azimuthal anisotropic parameters. So now we have a much better way to compare our tomographic results with the other anisotropic measurements from, for instance, from SKS model.
Okay.
So, but this wasn't done in my tomography.
Yeah, it's just that it's something that somehow I see that it was not really like you didn't have enough time probably to compare with all the other results and try to bring some understanding on all that. And then finally, like looking to your main results somehow, I think it was figure 12. Two things called my attention. One is the high velocities below the Borborema province at 600 kilometers. Can you comment a little bit about that?
Okay, figure number 12. Which
I think it's not in the presentation. Is that panel that you have the GLAD and your model all together?
Mm-hmm.
Yeah, but for example, this one, you see here in your model, you have kind of high velocity all over below the Borborema.
Mm-hmm. Yeah, but this is at 700 kilometers depth, so I wouldn't expect too much correlation between what lies on the surface and what is at 700 kilometers depth. I don't know the explanation for
Not
this.
really for the surface interpretation, but actually the transition zone, for example, Jordi, I think he has some papers that he didn't observe any variation on the transition thickness under this region, but you are showing some positive anomalies there.
Mm-hmm. Yes, I have to look into these papers and
like
think about that.
It's something, and the other thing, there are like comparing your tomography to the GLADs. It for me it's kind of point me out the limit of resolution for the GLAD model. Like below like 700 kilometers, the GLAD is almost constant, going deep, and your models do change a little bit, especially when you look to this figure 12 that you show. Like and the GLAD show two features that NWSE, like a northwest southeast, like two trend of blue velocities. Do you have an idea what is that? Your model also shows something like that at 800 kilometers, but then after, when you go deeper, this feature disappears.
Mm-hmm. You mean those two parallel structures?
Yeah, there is one that is the Nazca plates, but
yes.
There's another parallel one to the east.
Mm-hmm. Well, perhaps, and this is a big perhaps, I remember when I was talking about the Paraná plume, I mentioned that maybe those low velocity anomalies parallel to the Nazca slab are related to a mantle flow. So the Nazca slab plunging into the lower mantle is maybe displacing some hot material and creating some convection in this region, in this middle region. And maybe this convection is also affecting the other regions. So you have a hot material rising here, but then you can have a colder material on the other side. Perhaps this is a possible explanation.
Yeah.
So because it's parallel to the Nazca slab, so
it's exactly parallel.
Yes. So my guess is that it's somehow related to the Nazca slab. So that could be an explanation.
Yeah, I think that's an interesting first guess somehow, especially because they are really parallel, really parallel. And there is one last question that I want to make to you. And it's something like when I was hearing Ebru talking a little bit, and you talk about the amplitudes like starting to move from the phase measurements for the misfit to the amplitude. And something came to my mind is that not all the energy that we record on the seismogram is a ballistic wave. You know,
What
like
do you mean by ballistic wave?
like a phase. Like when you think about P wave or S waves, those are ballistic phases. They have kind of a predetermined paths inside the Earth, given by the kernel. There are also scattered waves, and those are not ballistics somehow. But when we move to the higher frequency, they are much more important in the seismogram because they create an envelope of energy arriving, but it's pretty hard to determine where they come from. Like, how would you deal with that somehow? Because like it's a feature that is interesting, and it's not very well studied by the seismologists somehow. There's I don't know too much people that really works with that a lot, but maybe this is something that will also push us to the next level, in my view. You know, that is studying the scattering from the deep Earth.
Yes, I think so, because one of the limitations of ray theory is that it cannot properly model scattering. So, and full waveform version can model scattering. For instance, the exponentiated phase measurement is very sensitive to. It's very sensitive to scattering. We can use the scattered waves, and I'm just starting to work with the envelope misfit function, but I don't know. Maybe it's also sensitive to the scattered waves. So when perhaps by combining exponential phase with envelope, we can really use that information from the scattered waves.
Yeah, most of the scattering is measuring on envelopes because you don't have an arrival time, and after you find the envelope of energy, it's pretty hard to find where it comes from. So this is something that I think it can bring maybe a next step, but it brings a lot of complexity to this. But somehow I was pretty impressed with the work, and I'd like to thank the opportunity to contribute a little bit to this. I would like to have more time and could contribute more, but I'm pretty satisfied, and I'd like to give you the congratulations.
Thank you so much, Professor.
Thank you, Carlos.
Thank you, Bianchi. So now I'm the last member to ask. I have only a few questions that remains. Caio, one thing that you tell in the paper, it's about you don't see the high velocity beneath the Rio de la Plata crater. So can you show the
Yes. Here.
Okay. So you also mentioned that this is not something that people see in other tomography models. And my question is, it's because you are taking maybe the Rio de la Plata crater lost his one part of his tectonic part of the lithosphere. It was somehow detached, and now it's like delamination. Because, for example, when you have some empty profiles coming across this part, and the MT shows a very resistive characteristics of this lithosphere. So why you don't see this feature in your model, in tomography model like yours?
You mean the H to H prime profile, for instance?
No, yeah, but no. Most of that profile that you showed, that map showing the Rio de la Plata, come back to yes. So why you don't see nothing here? If, for example, others methods are showing something, what you suggest? What's your guess?
Well, I know that's okay. So some people are using ray theory, and as I said, ray theory is an extremely useful method, and you can achieve a lot of things using ray theory, but you do have to be careful when using it, because sometimes people use ray theory in situations where ray theory does not apply, and that could create some artifacts in your model. So maybe artifacts is one explanation, but I don't want to claim that all models that have observed some features in the Rio de la Plata crater are just artifacts. I'm not saying that.
No. I think you didn't understand my question. It's you stated that all the other models are not showing also the high velocity beneath Rio de la Plata crater. So, but I'm asking you, for example, for another method, no geophysical method, other, for example, MT, magnetic-telluric method, okay, not any seismologic method, but why they see something beneath the Rio de la Plata, and seismology is not seeing nothing. Don't see nothing, okay?
Okay. Now I understood your question. I'm sorry. Seismic waves are sensitive to the elastic variations inside the Earth, and but MT method, they are more sensitive to conductivity inside the Earth. So the fact that we do not observe any feature in the tomographic model says that there is no sharp variation in the elastic parameters, but there may be variations in the conductivity, and I think conductivity could be affected by water content, maybe, but water should also affect seismic wave propagation. So yes, I don't know. Honestly, I don't know. So there has to be some property, something that is not affecting the elastic wave, or maybe there is a trade-off. Maybe there are two different factors in play. There is, for example, one factor increasing the seismic wave velocity propagation. There's another factor decreasing the velocity propagation. So overall, we don't see any change in the seismic velocity. But those two factors, they can be seen by the magnetic methods and by maybe electric methods. But I cannot think of anything right now, because yes, water should also change the seismic wave velocity. So any compositional change. Yes, I cannot think in any explanation, any geological explanation for this.
Okay, you have a slice at the depth of 150 kilometers. You are sure that you are seeing all the lithosphere?
No, the lithosphere, if you have a detachment, the lithosphere can be shallower than 150 kilometers. But I don't know the investigation depth of these MT method. I know they can probe several hundred meters in the mantle, depending on the wavelength they are using. But if they are seeing something very shallow, then yes, that could be an explanation, that I'm just looking very deep into the mantle. So I am below the cratonic lithosphere, because the cratonic lithosphere, the cratonic root was detached, and the other methods are more sensitive to shallower structures.
Okay. Is your model able to resolve shallower structures?
Yes, it is. And we can have a look at this. Yes, this is 80 kilometers depth. I am not trying to interpret anything above 80 kilometers depth, because we have the effect of the crust. And yes, we do see that it's a positive velocity anomaly region, but much weaker.
Just a bit. There is something. Just
further south or further north?
A bit more to south. Yeah. Yes. There's something, yeah. Okay. All right. So one difficult thing that we have here, or one thing that is missing for South America, it's a good lithospheric S model P or from P wave. So you just told us that it's very difficult to constrain the velocity of the lithosphere, because you can have some problems due to the crustal effect. Do you have any suggestion for a future work to improve this problem, or to solve this problem, so that you can have a very trustable model for the lithosphere beneath South America?
Okay. So you mean a...
Yeah, it's because the problems today we have the interpretation about the structure is because we don't have any reliable model for the velocity structure of the lithosphere beneath South America. Mm-hmm. So there is a lot of disputing regarding the position of a craton, of a certain structure. So you have some from you said that you have some problems regarding the using the shallow part of your model, because some maybe some technical problems or numerical stability. You have some clue how to fix it, how you can improve this, so that you can have a better model for the lithosphere?
No, it is not numerical instability. It's just that since we are adding crust 1.0 on top of our global model, and my tomography during the course of the inversions, I have a look at the crust, and the crust, we cannot really observe any significant change in the crust over the course of iterations. Most of the changes are going into the lower mantle. It's not that you are not updating the crust. It's just that beforehand you already had some very sharp velocity variations, and the new velocities you are adding, they are not changing that much the features that were already there. So if I try to look into my model, for instance, at 20 kilometers depth, mostly I would be interpreting crust 1.0. I'm not interpreting my model. Oh, the same goes to, for instance, 40 kilometers depth, I still have some regions in which I can see the mantle, but there are some regions in which the crust is already visible. So you have the crustal effect. So it's more a visualization problem. It's not a numerical issue with the inversion.
So what you can do to overcome this problem in a future work?
Well, that's a good question. I never thought about that before, because the fact that we are using the crust, that we are using crust 1.0, is a strength to our inversion, because we don't have to worry about crustal corrections. But on the other hand, we cannot really interpret the shallow regions of our model. We are mostly concerned with the upper mantle, not the very shallow regions of our crust. So I don't know. So perhaps if you could carry out an inversion without adding crust 1.0 on top of your model, but in that case, how would you take the crustal effects into account? How would you properly model the crust?
So, do you think that adding, for example, ambient noise to the adjointed would work and you'd fix it?
Well, yes, we are there are some. I know that we were discussing about that, about using adjoint tomography with ambient noise. So you can carry out a full form inversion using ambient noise data as well. But yes,
Caio, can I give you a hint?
yes.
What is the minimum period of your surface waves in the current simulations?
Okay. Yes, that makes sense. Okay, so now it's 17 seconds, the minimum. But
surface waves.
Yeah, surface waves. Well, I'm not separating the surface waves from the body waves. So actually, I'm filtering down to 17 seconds, but the actual periods are larger than that. So yes, maybe we have to, either we have to model higher frequency surface waves, or by using ambient noise, we can emulate higher frequency surface waves. So yes, that could solve the problem.
Okay. Well, I think one last question is, what do you think that is the most important contribution from your model or from your work?
From my model, I think it's the cratons. I think the constraining the boundaries of the cratons, and also constraining the thickness of the cratons. I think that this is the most reliable result we have from my tomography. But speaking of the entire work, I put a lot of effort into explaining what I have done. So I tried to make full waveform inversion more accessible, so other people can also begin working with full waveform inversion without having to spend 2 years just to understand the theory behind the method. So I think I have done an educational contribution with my thesis as well. So, and about the last paper, by the last paper, I mean the SP8 GOL tools. We also have, I also put some effort to explain the theory, to explain B-splines and spherical harmonics, but that toolbox actually makes our life much easier, because now we can really share these global adjoint tomography methods. I still have to work with an easy way to share regional tomography methods, regional tomographic models. For my model, I have used a block model, and it actually worked very well. But I may improve this eventually, perhaps using wavelets, for instance. But this toolbox will allow that other people can now use these adjoint tomography models, and can also improve the workflow of the adjoint tomography. Now we have a higher accuracy interpolation method. SpecFan already had a routine to carry out the interpolation, but and I perfectly understand the developer of the routine, because interpolation is extremely tricky, and SpecFan is a huge package. They already did a great work implementing everything they did. So the developers, they cannot spend 6 months just creating an interpolation routine. But I did this. I have to spend 6 months, because initially my goal was just to expand the GLAD models into spherical harmonics. But soon I realized that in order to expand those models, I needed an accurate interpolation method. And so in the end, I had to develop a high accuracy interpolation scheme. And this is also a very important contribution. So yes, so over the course of the years, my main project has branched out into several side projects, and each of these projects has some contribution. So there are different kinds of contributions.
Okay, so just one quick question, last quick question. It's when you correlate the lab models, why did you correlate the lab model from Priestley with your models? because you only show the correlation with surface with receiver function dots, but not with your model itself. Am I correct? Because I see a good correlation, but why you didn't correlate? The Priestley model is the CAN 16.
Oh, okay. So, yes. So that part of the work was mostly done by Professor Marcelo. So
Okay.
he actually was the one who did this correlation. In the beginning, I was just providing the lab, the LAB model. We were trying some different levels of smoothing, and in the end, I found a nice way to create this LAB model, because finding the gradient jump is not that easy, because you also have the morro. The morro is a much stronger jump, and you have to make sure that you are not selecting the morro rather than the LAB. But in the end, I sent him my LAB map, and he did some further processing, but he was the one who actually carried out this correlation.
Okay, that's great. So I think I don't have any further question for now. So congrats, Caio, for your work, for your presentation. I followed all your life here during the PhD. It was a very hard but very good work you delivered. Now, thank you, Marcelo. Congrats to Marcelo as well, and Ebru for helping Caio during this rolling project. So I think we don't have any further questions. Marcelo, would you like to add something?
No, I'm fine, thanks.
Okay, so that's it.
No, perhaps I should mention that most of the supervising was actually done by Ebru and Suzanne van der Lee. So, and Caio did most of the learning by himself. So it's very easy to supervise him. Okay.
So, okay. All right. So you next to change the room now.
E aí, Caio, tá cansado aí de tantas horas aí respondendo?
Na verdade eu achei que fosse ser até pior. Estava esperando perguntas até mais difíceis. Mas, tô cansado, sim.
Cansa assim, fisicamente e mentalmente, ficar se concentrando em tudo, né?
Uhum.
Tá bom, acho que você foi muito bem na exposição e nas respostas. Então.
Muito obrigado, professor.
So Caio, we have we talk a lot. about your defense. So yes, you are approved. Okay, all the members say that you performed a very nice work. So thank you. You are approved. You are a PhD.
Congratulations.
Thank you.
Congratulations, Caio. Very good.
Okay, I think that it's all. Richard, something else? Okay. All right. Okay. Yeah, I know your mother is there.
Yes, certainly. No, I just thank everyone that has been watching me, because those defenses, they are very overwhelming. So you have to be very, very brave to watch a full defense. So thank you a lot for withstanding such a long time.
Okay, so these are the final words. Okay, say Daniel.
Yeah, I'm just curious, where are you headed after your PhD?
Oh,
Yeah. Sorry,
that's a good question.
Okay.
can you repeat the question? Sorry, I was distracted.
I'm just curious where you're.
Oh, so sorry, Daniel.
I'm just curious where you're going next.
Oh, I'm working with Professor Ebru already. Right now I have a strange postdoc position, mostly due to COVID-19, because I cannot move to the US yet. The boundaries are closed for Brazil. For now, we are working to several smaller projects, but eventually I want to move to Colorado School of Mines again. I have been there in 2018 and 2019, and that's the plan. So the project is related to source inversions, also a bit of full-form tomography again in another region. I am helping my friend in Turkey with the implementation of these other adjoint sources to work with azimuthal anisotropy, attenuation, and eventually I want to move to normal modes.
Okay.
Well, good luck in Colorado when you get there.
Good luck with that.
Thank you so much.
Yeah. Ask Straheisen to build again the STS-1 so you can have measurements to work with normal modes.
Thank you.
Okay, great. So I think we're done. So thank you all for joining us, for all the questions, for the contribution. Okay, so see you all around.
Right.
Yeah. Thank you, Carlos.
Thank
And
you.
congratulations,
Thank you,
Caio.
everyone.
Bye-bye.
Congratulations, Caio.
Bye-bye.
Bye-bye.